Some of it. Thank you, Jan. Thank you. So it's the last talk of the day, so you must be tired. I'll try to ask a few questions at times to wake you up, but please make it interactive. I think it's best for everyone. So the abstract was a little bit short, just one line, so apparently it was not the only one, but I was not quite sure what would fit in the presentation, so that's why I kept it as a mystery until the last minute. But in the end, I want to kind of demystify what polyhedral compilation means. So I won't go into lots of detail, but I will give you some concrete stuff, because some people may know the word, but not necessarily have a precise view of it. And I want essentially to stress the kind of compiler construction aspects. I'm not going into like details of linear optimization algorithms, etc. I want to explain why it's useful in general if you want to build optimizing compilers, especially for high-performance computing or machine learning, and not necessarily like the details of some specific techniques. So why polyhedra first? So I think maybe the most obvious reason today to see programs as polyhedra, there are many in static analysis in other domains, but in what we are talking about today is tiles. So there are tiles everywhere, even on the floor. They are a bit complicated, actually. There are rather boring tiles, like just rectangles. There are more fancy tiles, not necessarily periodic. And just a quick show of hands in terms of human imagination or illusion. How many of you read design patterns there? Okay. So it's pattern design, unfortunately. But so we really care about design patterns and not so much about pattern design. Actually, we're going to go through very stupid shapes of tiles, essentially rectangles and combinations of rectangle tiles. So there is no way we are going to deal with these kind of fancy things here. Why is that? So tiles are everywhere. In hardware, as you can imagine, the way we build larger systems is by putting together smaller pieces like cores, memory dies, memory IPs, etc. that we understand. So the TPUs from Google, for example, on the cloud are not an exception. So these are very high-level abstractions of the machine learning accelerators from Google. So these are the ones used for training, so including floating point units. And there are like this kind of high-level vector abstractions that are two-dimensional that map to, or you can see them as systolic arrays as well. They are called in the hardware design, and they are mapped to like smaller grain, finer grain functional units that do typical arithmetic, like additions, multiplications, etc., activation functions for neural networks in hardware, and the proper memory interface to deal with this. So the tile architecture is all over the place in terms of, let's say, instruction set, if you want. This is the case for many other designs. So like so-called the edge computing area, you will have lots of accelerators that will deal with like signal processing, machine learning, radio networks, etc. And for example, in the area of machine learning, you have all this zoo of processors from Movidius, which is Intel also now, Intel itself, NVIDIA, Google, etc. You can buy those things for usually a few tens of dollars or euros, and they consume milliwatts to a few watts. And every one of those accelerators, they are very specialized. Usually they don't have floating point units. They have like 8-bit fixed point numbers, integers, or they may have even more obscure 1.6-bit encodings for like Boolean neural networks or ternary encodings, etc. So you need converters that go from high-level graphs operating on like matrices, tensors, arrays, etc., of floats, and convert them into those odd representations. So you need compilers for that. You need to optimize the computation for the shape of those machines. They are tiled, so you need to block the computation into smaller pieces that fit on the memory of those machines. And the chips themselves are tiled internally, so you need to further decompose the code and the data so that it fits on those machines. So there is a lot of adaptation to go from a high-level computation to this kind of hardware, and most of it has to do with tiling, like essentially decomposing computations and data in blocks. And this is just for decoration. And one of the aspects that is often overlooked is the data layout itself. So if you, for example, if you work in the area of machine learning, but that's also the case in high-performance computing, you are dealing with libraries or hardware accelerators that make some assumptions about the data layout. So you can assume, for example, if you do linear algebra, you have the BLAS routines that do matrix product, matrix vector products, and some more advanced things like LU factorization, etc. They all assume some like row major or column major encoding of data, and some ability to stride through the data to implement like block-wise operations, like block matrix product, blocked LU decomposition, etc. So it's the same for machine learning layers, whether you want to implement convolutions or other specific layers in neural networks. You have these kind of specific constraints. And again, no mystery. Those constraints are typically enforced through blocks. So you have to decompose the data itself, organize it into blocks. For example, this is an example from the XLA domain-specific compiler that goes with TensorFlow. If you start from a high-level neural network description in Python or some let's say, high-level view of the data that makes the tensors in the layers, you have to decompose the data into blocks that will fit the implementation of the libraries for matrix product, convolutions, etc. And those blocks will depend on the data size and type. For example, if you're dealing with float 32, you won't necessarily have the same layout as if you are dealing with float 16, like very short floating point numbers, or if you're dealing with 8-bit ints, etc. So all these layout considerations, again, I don't go into the details of why this is better or worse for some architectures. They again get encoded in this kind of polyhedral tiled layouts. That's best seen in some of the domain-specific languages that have been designed for these high-performance computing applications. So maybe some of you have heard about the Halide image processing DSL. How many of you heard about Halide? So it's originally from Adobe and MIT, but it's heavily used at Google and some other places, mostly for image processing, like camera, HDR pipelines and stuff like that. And it's used not only on general purpose processors, but also on DSPs and like accelerators in smartphones and other things. Qualcomm, for example, has a pipeline for the DSPs. Here the idea is that you want to play on both sides, both control and data. So you want to block the computation such that you will not traverse the full image, but you will traverse a small block of the image to fit some local memory constraints, for example. Let me introduce a little bit of vocabulary. When we say strip mining, this is actually taking a long dimension of something, an array, an image, a tensor, and decomposing it into stripes of fixed length. Like, for example, some vectors or some smaller block within the dimension, but it doesn't include permuting the iteration space. It doesn't include saying, I want to shortcut the iteration of the line before going to the next line. This is permutation. This is an additional step that will get you into the proper tiling. Strip mining is only decomposing into these kind of sub-blocks, and when you combine it with this permutation, you get this tiled iteration traversal. Just some reordering effect that strip mining does not encode. So when you do that, you can go further and say, okay, now I want to instantaneously execute those stripes of, for example, here 4 iterations or 4 data elements, and run them into a vector architecture. So if you have SIMD instructions, vector instructions on your Intel processors or AMD processor, ARM processors, etc., you will take advantage of this transformation to enable vectorization, and some compilers do it automatically. And you can do more fancy things. That's why the Halide is a DSL, and it's like specialized for image processing pipelines and not a general purpose compiler. It does very strange things like computing twice the middle element of a row of 7 elements. So for example, if you have 7 elements to vectorize, you're not going to decompose it into 2 parts of equal size. There is no way you can do that because vectors typically don't have 7 elements. So either you do extra work on the side. You say, okay, when there's an extra dummy element that I will compute nonsense of it and drop it in the end, mask it out in the end, or you don't vectorize. Typically, you vectorize only a part of the data, but not of the computation, but not everything. Or you do this kind of domain-specific trick of shifting one of the vectors by 1 to the left and effectively computing running the computation twice on the middle element. So this is one of the ways to vectorize using Halide, for example. Okay, so because of all these tricks, you can imagine that some programmers have been very happy to implement this by hand in using like assembly level hacks, essentially. You want the compiler framework to actually make this more abstract, and that's one of the reasons people design these domain-specific languages to deal with these special cases. There is another very similar framework to Halide called TVM that you may also have heard about. So if you have heard about TVM but not Halide, that's bad. That's because there is some communication effort that tries to blur the lines, I would say, but originally TVM is actually very similar to Halide, but adapted to machine learning, and it's actually a forked code base. So it's the same idea, so you can build domain-specific pipelines of layers in neural networks using the same kind of API approach as an abstraction approach as Halide. And this is actually a code example that does it, so I can very briefly explain how this works. This is to implement one cell, meaning a series of tightly coupled layers in a recurrent network. So I don't have to explain what a recurrent network is. This is not important for this talk, but that's an important, let's say, basic block in a neural network that you would use for natural language processing, for example. It has two parts. That's the important thing. So you could see this as Python or C++, or the syntax is very similar. You have a compute part that describes the functional semantics. So basically, what array or what vectors or what matrices get loaded, operated upon with a lambda expression that describes the basic arithmetic and stored in memory. And you have a second part that schedules it, quote unquote. So essentially explains how to lower those functional, those kind of denotations into some operations that match the architecture that you want to run it upon. So I don't know how many of you are familiar with CUDA programming or like GPU architectures in general, even if you didn't write much GPU code. Okay, so that's a small minority, but not negligible. So I don't want to go into the details of GPU architectures here. What I want to tell you is that essentially it's a very hierarchical programming model. So unlike like multi-threaded programming in Java or POSIX or whatever, the threads on the GPU are very hierarchically laid out, and the data as well is organized in a very hierarchical way. And no wonder this hierarchy is very much tied with like tile-based organization. So in CUDA it's called blocks and threads. So blocks are like coarse-grained threads, essentially, scheduled by the processor. So you don't necessarily understand how the blocks can be arranged dynamically. This is the GPU hardware in charge of doing that. And threads are finer-grained concurrent elements that are essentially functioning in lockstep. So you can see them as a way to process element-wise in vectors. So instead of seeing a vector operation as a black box, like a map or reduce operation on a short vector, the threads will give you a more like scalar view of things, more like element per element view of more like an iterator, essentially to work on the vectors. And again, the hardware is responsible for combining these threads into so-called warps, meaning essentially hardware like dynamic vectors of operations that will run synchronously, that will run in a single clock cycle. So that means as a programming interface, you have to decompose the high-level maps and reduce and whatever computations you have there into this hierarchy of blocks and threads. And you don't have only one block and one thread dimension, you typically have three. Why three? Because you have images that have two dimensions, and sometimes 3D graphics also come into play. Don't forget, GPUs were primarily designed for graphics, although now they are primarily designed for Bitcoin mining. Sorry, that's over already. So this is one of the reasons it's a real pain to program those things. You have to completely get away from the software engineering principles you have learned at school in terms of using higher order functions, abstraction layers, etc. Think about the functionality and reuse first. Now it's the exact opposite. You have to think in terms of hardware features, completely tune the iteration space, the organization of the data itself to the constraints of the hardware, and essentially re-engineer your computation to fit those constraints well. Otherwise, you don't get any performance. Okay? So the schedule is there to ease that process. So it doesn't get away from understanding mentally as a programmer the constraints of the hardware, but at least it makes the lowering from the denotations to the operations much more, let's say, reusable and productive. So you have this kind of splitting constructs that will tell you essentially how to strip mine the computation, decomposing it to blocks, and then how to bind the different dimensions that result from this strip mining to the different levels of hierarchy of the threads and blocks. So in this case, you would say, I get two dimensions from strip mining one dimension of an initial vector, and the first dimension I bind to blocks, and the second dimension I bind to threads, and this way I get parallelism running on two levels, essentially coarse-grained parallelism, and the second bind method will exploit some finer-grained thread parallelism, meaning vector parallelism, really. And you can do that several times. You can compose these transformations to some extent. That's another issue. I will come back to it later. And eventually, when you're done, magically, all these operations operate internally on some AST, on some abstract representation of the denotations above, of the computations, and that will be lowered to some low-level intermediate representation. In this case, LLVM IR. Okay, so this is no big deal today. It's principally a great engineering, I would say, great design for principles that have been there for a long time in like embedded domain-specific languages and high-performance computing, but this is made accessible to people who don't have a clue about how to write compilers, essentially. So we can do more than that, and we have to do more than that. So tiling is great, but it's not enough, essentially. That's the story. If you look at real problems, in general, you don't know the size of the problem beforehand. For example, in high-performance computing, most of the libraries, they take care of arbitrary sized matrices and arrays, and also the strides between successive rows in a block, for example, of a matrix, block matrix multiplication, are not known statically. They're not known at compile time. So you want to expose this kind of symbolic reasoning capability to the compiler as well, not only the library implementation, but if you want to generate this library code, for example, or if you want to orchestrate multiple library functions in a compiler, you have to reason symbolically on all those bounds, on those sizes and shapes, etc. Sometimes you even want to be rank polymorphic, so, or dimension polymorphic in terms of, I don't know if this is a vector or matrix or tensor or something. If you wrote MATLAB code or NumPy code, you're familiar with this kind of genericity. And you want much more than tiling. You want to fuse loops, typically. So that's very intuitive. So if you implement a neural network that's composed of alternating sequences of convolutions, just like stencils, think of I'm taking neighboring data and multiplying them, adding them, and activation functions, meaning like hyperbolic tangent or non-differentiable like very simple functions, essentially, that operate pointwise. It's very easy to imagine that you get much better performance by fusing consecutive layers that will operate on the same data. That will save cache usage, or that will make use of temporal locality in caches much better. I have some examples about that later. That's a very basic transformation you want to apply, in addition to tiling and organizing the data in blocks. You also want to do pipelining to hide latency. I guess you are all familiar with instruction pipelines in processors. So you can do the same thing at a much coarser granularity, like loading a block of data while another block is being computed, some kind of double buffering scheme. You have to organize this statically in the compiler. You have to implement program transformations that express those things. So you need a framework that's very capable in terms of symbolic reasoning on array elements, on loops, and also on modeling the hardware resources that are being accessed in the meantime. You want to do this in a composable way, because it's not just one trick that will make you run fast. That's very clear from the halide schedules or TVM schedules. You have practically to write a chain of tons of scheduling decisions to actually decompose your high-level denotations into something that runs fast on a GPU, and even on the CPU, which is like a multi-core processor, which is apparently a simpler beast. You still have to do lots of things to get good performance. And some of these transformations may be incorrect, because you may, in your head, think, oh, I want to do that, but you forgot about some dependencies or some races that will arise in this optimization. So you have some consistency checking involved into that. So the programmers may think of something, but that's not actually correct. You want tools to support that as well at compile time. And in many cases, you have no clue what's profitable. So making sure that you run fast means tuning some parameters very precisely. For example, it's clear that you want to group computations and data into tiles, but what's the right tile size, for example? How big should be these local computations? That really depends on the on the hardware. So it depends on how much cache memory you have, how wide your vectors are, etc., etc. So this is a big challenge for compiler construction because usually you don't have all these things abstracted in a kind of cross-language, cross-target hardware manner. So if you use LLVM IR, I don't know how many of you have looked at the kind of low-level representations that most compilers use today. It's very hard to reason symbolically on multidimensional arrays. There is not even a notion of a multidimensional array in LLVM right now. And even worse, to transform the loop nests in such a way. So we need more than that. And essentially, we are saved in a way by the simplicity that I mentioned at the beginning. So the practical tiles and transformations like fusion, pipelining, etc., that we are dealing with are much more than like the boring stuff on the left. Sorry, so the semi-boring stuff on the left, and not at all like these crazy decompositions on the middle and right. So what we can do is essentially abstract those symbolic reasoning problems, like analysis transformation problems, as polyhedra. What are these polyhedra? They are just geometric views of the program. So you take all the iterations of loops, all the elements of multidimensional arrays, and describe them using systems of affine or linear inequalities. So you say, I want to carve some block of an array by saying, I want all the elements between abscisses 4 and abscisses n, and ordinate m and m prime or something like that. And you can do more fancy things like any linear combination of indices or element index positions in the arrays and loops. And that's very powerful because as we will see, you can actually compose quite sophisticated sequences of transformations. You can say, I want to incrementally refine my program so that it runs fast on this particular architecture model. You can represent this as a geometric transformation, essentially a series of like tiling levels, so you decompose into smaller and smaller blocks, and very careful like realignment or pipelining decisions, fusion decisions, etc., etc. So that's the good news, and I will give you some concrete elements for that. And it's also very nice to describe the resources that we have to deal with. The first one is time. So how do you organize the computation over time? Now we are not dealing anymore with like an inductive while loop or recursion that will rewrite itself into the next iteration or something like that. We are dealing with a flat structure that's just all the iterations from 0 to 42, for example. So it's a much more geometric and flat, more algebraic way of reasoning. And same thing for space. So if you have a grid of processors or a grid of like 2D or 3D grid of threads, you can model it very naturally using these geometrical shapes. That's very clear. And same thing for memory addressing. So let me zoom in on what it means in practice. So a little bit of math and examples to show you that. And that's joint work with colleague Alex, and also summarizing some work from different papers. I have a list of references at some point. So as I say, the main motivation for modeling programs as polyhedra is this mess that comes from the hardware. So you don't want to deal with that as a programmer, but at some point the compiler needs to deal with that. It needs to model it. So for CPUs, you typically have to deal with 3 levels of parallelism, from high level like POSIX threads down to instruction level parallelism and vectors. For GPUs, you can go up to maybe 8 levels, so you have the same stuff, and also higher levels of work groups or blocks and threads. And this makes obviously the optimization problems more combinatorial, but fundamentally it's the same kind of geometric decisions you have to take. Same thing for other hardware accelerators, like the cloud TPUs from Google. They would also work with different abstractions, but the same kind of problems have to be solved. Same thing for the memory hierarchy itself. So you know about caches, but caches don't come in a flat way. They come in hierarchies. So you have an L1 cache, you have registers also that are very close to the functional units, and then you have last level caches that are much bigger and slower. Sometimes you have also different types of main memory. So you have to address all these effects here in terms of so-called locality, temporal and spatial locality, and I will give you some examples on that. How many of you know these words, temporal locality, spatial locality? A majority, but not everyone. So I will have an example. And one very important aspect of these memory hierarchies is that it hides latency. So the memory is slow, When you're close to the functional unit in the processor, obviously it's fast. It's just maybe a few cycles to access it. When it's in main memory, it can be 200 cycles to access it, especially if it's large blocks you want to transfer. So those caches are there to hide latency, but they are also there to improve bandwidth. So the number of bytes you can get per cycle or per second from the registers can be 100 times more than from the main memory. And that's a major architecture trade-off. For example, comparing a high-priced NVIDIA GPU for Bitcoin mining with one that we would have in your phone, the biggest difference is not so much on the computational aspect, is how much memory bandwidth it can transfer practically. And that, of course, heats a lot as well. So that would not fit in your phone. So there are interesting effects of caches, but also negative effects. As was mentioned before, they have lots of security issues because they leak information in all these fancy microarchitecture mechanisms. But those fancy architecture mechanisms, including, for example, the address conflicts that were mentioned before, they also translate into performance problems. So we have to make sure that there are no conflicts in what we hope will be stored in the cache at any given time, not because of the cache capacity, that's something we understand rather well, but because of the fine-grained mechanism that the cache implements to replace the words or the lines in the cache when they age, essentially. So you know about cache replacement policies, you know about how the memory addresses are cast into tags or some essentially ways for the cache to recover which line holds which data. So there are lots of tricks there. Also across caches, when you have multiple processors, cache coherence is a very big problem. So these are some effects that the compiler also is supposed to mitigate when you want to generate high-performance code. Again, the good news is that those effects can be modeled in most cases as at least or approximated using these geometrical abstractions. And there are many other aspects I don't have to deal with, but if you are familiar with vector processing, you know that also alignment is an issue. So whether the data starts at a multiple of the vector length or page size, if you have virtual memory or whatever, this is important as well, so we also need to model these things. So a few concrete examples if you're not familiar with computer architecture. Temporal locality and spatial locality, they are very common concepts in caches, but also in let's say in general in all kinds of local memories that you could be managing in software. It doesn't have to be a hardware cache. Temporal locality means that over time, the same data from memory, so at the same address and the same data will be reused more than once. Okay. So typically, you expect that the cache capacity will be large enough that in between two accesses to the same memory element, you will find the data again in the cache. So you won't be evicting that data because the cache is too small. Okay? So that's called temporal locality. And the more you essentially exploit it, the more useful the cache capacity is actually, the more usefully it is exploited. Okay? You don't want to store in the cache some essentially old data that won't be accessed anymore. You want to make sure that the data that is there is going to be reused sooner or later, or better soon, because that's why you want to have it cached in the first place. Spatial locality is a little less intuitive if you're not familiar with cache lines. The word was mentioned earlier. The fact that the cache is not organized like in terms of bytes for obvious reasons, because for every element in the cache you have to essentially record, like in a hash table, where it comes from. So a cache is essentially an associative table that records mapping between memory addresses and elements that are stored in the cache. So for every data that you store in the cache, you have to remember where it comes from. So if it's at the byte level, you're going to spend a huge amount of space to remember the addresses along with the elements. So we don't do that. Instead, we have larger cache lines. We also do that for bandwidth reasons, so that more data can be fetched from the cache at any given time in a given cycle. And that has some benefits as well, because most of the, let's say, well-organized data structures, they are organized contiguously in memory. So even if you work with linked lists or graphs or whatever, in general, it's a common optimization, because people know that, to make sure that the frequently loaded elements from the data structure are stored consecutively in memory. And that's because they will be stored in the same cache line or cache lines, in a few cache lines, if not only the same cache line itself. So for example, if you're doing, if you're storing a matrix in memory in a raw major way, like in the C language or most languages except Fortran, you would make sure that you traverse the data in the matrix by scanning through the columns of a row first before iterating on the rows. Because within the columns, you have consecutive accesses in memory, while within rows, you may have to stride along different cache lines. Okay? So the consecutive columns will fall in the same line. There is some special locality there. It's called space because it fits locally in space in the same line. Across rows, it's not the case. I hope this is clear. So if you want more examples, I can explain more, but I think for most people, it's standard stuff. Fault sharing may not be as familiar to you. So if you have more than one processor or more than one thread accessing different caches, so there are some protocols that will keep those cache lines coherent. Essentially, they will make sure that if one processor or one thread modifies the data, then the other thread is notified in case he wants to access the data, so that it accesses the right data. So there are some consistency models for memory that will define what coherence actions have to take place, but that's not the problem here. Essentially, this is implemented in hardware typically. The problem is that because we have these cache lines, the coherence protocol is not able to deal with individual elements of memory that are being addressed concurrently. It has to transfer the full line. And in case you are, for example, dealing with two threads accessing two parts of the same cache line, you'll have a spurious ping-pong effect between those two threads. So one of the threads may modify the cache line. The other thread thinks that the data has been modified. It's not the case because it's a different element in memory, but it belongs to the same cache line. So because of that, the processor has to transfer the data back and forth. So we also have to model these kind of effects on at least on processors that have caches. That's also the case if you're dealing with computations that are not perfectly partitioned. For example, matrix product is perfect. It's just block-wise operations. But if you apply like convolutions or like stencil operations on images, you typically have shadow arrays of memory that are accessed simultaneously by multiple blocks of or multiple tiles of computation. That's because the computation itself accesses neighboring elements. Like you apply a Gaussian blur on an image, you are looking at the neighboring elements to compute some mean or something. So that also creates some kind of software-induced fault sharing and communications that have to be modeled. And the last bit is so-called coalescing. So that's terminology from NVIDIA. But it's very similar to spatial locality combined with vectorization. So essentially, to get good performance on GPUs, you have to make sure that your data is spatially local, so it actually falls in the same regions of consecutive addresses, and also it's accessed simultaneously by threads that are indexed in a certain way, essentially the fastest varying dimension of threads. And if the two are aligned, like the memory, the storage is well aligned with the thread indexing, you can essentially load all this data or store all this data in one cycle. Okay? And if it's not perfectly the case, then it needs more time, and the hardware deals with that. So it's abstract, it's opaque. You don't have to deal with it if you want correctness, but if you want performance, you have to think about those things. Essentially, making sure that the vectorization or the threading mechanisms are well aligned with the storage of data. So that's typically that's the main mistake that programmers do when they port legacy code to CUDA is to not understand that, mix up the thread dimensions that have to go into coalescing with some other sequential loops into threads or whatnot, and they just don't get this. So you want this to be managed by a compiler ideally. So to summarize, I think it's clear to you now that you want a representation that makes compiler capable of reasoning about all these things. So that all these things are individual array elements, not just full arrays as a scalar opaque object, but operating at a single array element level. Same thing about loop iterations. You don't want to see loops as one like big combinator that maps or reduces things. You want to do maybe individual things at individual iterations. Also relations between these and relations between iterations and array elements with hardware resources. So like the mapping of those computations and data to the specific threads and blocks and whatnot have to be also modeled in the compiler in a symbolic way. Symbolic because we generally don't know the sizes of everything. So there are programming languages to do that. So for example, if you do NumPy in Python, or there are math libraries for all kinds of languages, there are nice abstractions for that. And you can even reason at high levels in terms of optimizations for these abstractions. But that doesn't really help with the hardware resources. That doesn't really help with how the memory is organized and how the resources are distributed over time and space. And also, you want this to be typically abstract in a portability sense. You don't want to think, even if it's a nice level of abstraction, you want it to be portable across machines. So some of the decisions, like figuring out the right level of parallelism and the right level of nesting of tiles, is very target dependent. So that has led, as I said before, to the design of some domain-specific approaches, and I list here a few more languages in the field of machine learning. Like TVM is and tiramisu are very close to halide, but there are other languages, I will talk about tensor comprehensions in a minute, that are also trying to address all of these issues. So how to model both the abstractions and their mapping to the hardware, and how to make it performance portable. So if you move from one hardware to another one, you don't want to redo the optimization. And it's tough to do that, not only because it's difficult optimization problem, but because it's hard to figure out what's the right representation for this feature. So how to essentially reconcile all these needs into a single semantical level of abstraction is difficult, because it wants to model high level like algebra of math and very hardware specific things at the same time. And ideally you also want it to be usable in a general purpose compiler, like GCC, Clang, ICC, etc., and in a domain-specific framework that's more aiming for the best possible performance, typically. So let's try to picture this in a more graphical way. So in general, when you write high-performance software, you have two approaches. One is essentially the best effort approach on the left. So you have a hammer, okay? It's like LLVM IR and SSA-based optimizations. I know how to do constant propagation, I know how to do register allocation, etc. So I'm going to try to tune these things a little bit such that for my new domain or my new target hardware, I'm going to get better performance, okay? So you have limited amounts of resources in terms of engineering skills, understanding of the code base, whatever. So that's what people do. And ICC has been evolving since the 70s, and GCC since the 80s, and LLVM more recently. But essentially, all these frameworks are general-purpose compilers trying to do the best of their existing infrastructure. So it's the sort of case of some more domain-specific compilers, Pluto and PPCG. So Pluto is the state-of-the-art, let's say, parallelizing compiler using polyhedral techniques. PPCG is some tool that we did at INRIA before I left for Google that does the same, but more specifically for GPUs. These essentially, they are more specific because they use polyhedral techniques, but they are still very generic in the optimization objectives. They don't necessarily try to support a specific domain like machine learning or image processing or something. So they have one common heuristic that tries to address all problems. And we'll see that's not always sufficient. And then you have the complementary approach. So maybe some of you are working on domain-specific languages, especially here in the field of high-performance computing. I'm thinking of domain-specific languages that make modeling hardware resources more easily, more practical. And here are a few names. So Polymage is a little bit like halide, but fully automated using polyhedral techniques. If you want to look at it, I can give you some references. So the approach is to acknowledge that, okay, we don't have a hammer. Instead, we start from the bottom. We have nails. They are not nails, actually. We have screws. And we look at the screws very precisely, and we try to find the best tool for each specific screw. Okay? And that may end up doing like replicating some work. Oh, now I have to think of my register allocation 3 times, or 5 times. Each time I change the screw, I may have to redo the work, or I have to re-engineer my compiler. But it's going to be a much smaller compiler. It's going to be a compiler dedicated to a particular domain and maybe a particular screw. So it's probably much easier than trying to solve all the problems of compiling C and C++. Okay? Obviously, there are some trade-offs between the two. The reason I'm selling polyhedral compilers as a design pattern is that I think it's essentially a building block for building whichever tool that you want. So it's used in classical compilers, like LLVM has a project called Poly that uses polyhedral techniques, poly with 2 L's because of LLVM. Okay? And at the same time, it's using domain-specific compilers, and I will highlight one later called tensor comprehensions for machine learning. And the reason is that it's capable of dealing with all these challenges I was listing before. It has a high level of abstraction to reason about array computations and loop nests, and it's also able to capture hardware-specific details and the relations between the two. And even if you're doing a domain-specific framework, you don't necessarily want to start from scratch at every new challenge that you're addressing. maybe you heard about the Scala metaprogramming framework called LMS, lightweight modular staging. So this is typically the kind of framework you want to design to facilitate the implementation of domain-specific languages and compilers. So there is a lot of motivation for building frameworks that are reusable across domain-specific languages, and this is one of the advantages of polyhedral compilation. So let's go into the details now, into the math. Let me see how much time I spent already. Okay. A typical example I mentioned before is a convolution. In this case, it's a two-dimensional convolution. We'll also use the linear algebra examples later. So you have 4 nested loops. This is a C-like syntax. You initialize a target array, two-dimensional array with zeros, floating points. And then you have typically smaller loops inside that iterate within a window. Okay, so it's a sliding window that will essentially apply a convolution local to relative to this position I and j, and store it into the output array C. So the window has 2 parts. It has the window that effectively, the window computation has two factors. The first factor is effectively sliding through the image, for example, or a tensor used in a neural network layer, and it has the weights in a neural network language, or the kernel coefficients in a more signal processing language that are going to be multiplied with those. So if you apply a Gaussian filter typically to an image, just to do like a 3x3 Gaussian blur of an image, you would typically have kh and kw equal 3, or you would go from -1 to 1 or 0 to 2. I mean, it's up to you. And you would multiply with 0, 1, or 2, depending on where you are, or 4, sorry, depending on where you are on the kernel of coefficients. Okay, so essentially it's a kind of weighted average of the window. So this is a very specific pattern. The values here can be much larger, so you can have like 11 by 11 kernels, or even larger than that. One of the typical optimizations here is to specialize for those sizes. So maybe the image itself may be large and parametric, symbolic, but it's very often the kernels are fixed size, and you may want to, for example, fully unroll those loops. But that's not the programmer who should be responsible for doing that. The compiler should decide whether it's profitable to unroll those loops, simplify those expressions, vectorize them, etc., etc. So at a high level, it's very easy to understand this code. What you want to do in terms of optimizations very much depends on the target, depends on the size of those parameters, if you know them, etc., etc. So in terms of polyhedral compilation, this is how we make it a geometrical shape, let's say. First of all, you have to name every computational statement. So we don't care about loops. The loops will go away. They will become constraints, just like inequalities, equalities using linear arithmetic. But the actual numerical computations, we call them statements. Okay, so this is statement S1, and below this there will be statement S2. And we can think in terms now of instances of those statements. So if you unroll the I loop, so I start from 0, I start for 0, then I goes 1 to 1, etc. You still have the J loop inside, and I skip the rest of the code. You want to attach different properties. You want to take potentially different decisions for every iteration of the I loop. So think of it as virtually unrolled. You are not going to really replicate the code in general. That's kind of crazy, unless you know that the number of iterations is small. But you want to symbolically reason about every individual iteration of I in a finite way. People call it a finitely generated, like implicit representation of the iterations. You can do that twice, okay? Again, for iterations of J. You may want to do this for all 4 loops. We call these things statement instances. So that's the vocabulary that is commonly used in this field. So a statement instance is just an abstraction of the runtime execution of a statement. So this is very trivial. Basically, in a general purpose language, you have an operational semantics that will tell you about the states of the machine, of the environment, etc. And these are just like states in a state machine. But in a geometrical way, we are going to model these instances as vectors in vector spaces, and they're going to be linear functions that implement relations between these iterations, typically. So that's why we are defining a specific vocabulary for this. And we group together all these iterations, so all these instances of statements, into so-called iteration domain. So that's terminology from the 80s already. That's essentially a symbolic way of representing all these sets. Okay? So for statement S1, all the iteration domain of S1 are all the iterations of statements of the statement that initializes C, indexed by two coordinates. So it's essentially it's a vector space of dimension 2, where the number of iterations is the size of the vector space is h minus kh multiplied by w minus kw. Okay? So it's just a vector space. You can see it graphically like this. So you have essentially I and j two-dimensional iterations, and the game here is not to explicitly unroll all these points into this space, but to represent it in a finite way, using inequalities and equalities and only affine forms, linear and affine forms. So there are libraries for doing that. Fortunately, we don't have to do everything from scratch. For example, you may want in general to reason about integer sets in a finitely presented way, not enumerating them. And you may want to ask questions about, is this set empty? Is this intersection of two sets empty? Please compute the difference between one set and another set that partially intersects it. Or please project away one dimension of the set because I want to know the footprint of some array block being accessed by some loops over some instruction, for example. So all kinds of geometric problems this way, of this kind. And you may want to solve some optimization problems, like please minimize that function over this set. I want to find the iteration that accesses the element of the array that's closest to the beginning of the array, for example. That's the lowest memory address for some reason. Or I want to find the iteration that executes first. Or I want to find the function that minimizes the number of steps it takes to execute this loop nest. So you have all kinds of optimization problems to be modeled in a geometrical way using these abstractions. So there are libraries for that, and the most advanced one, the state-of-the-art one, is called ISL. By your colleagues Van Verdolegge, with whom I have collaborated for about 10 years. And this is the syntax it takes, for example, to model the iteration space of S2 using ISL. So that's derived from a former project called Omega at the University of Maryland. So it's a complete rewrite because the algorithms are completely different, but the syntax has some connection with Omega. And I guess this is kind of readable. So you have a vector that is named by the statement. So this is the vector part, but there's also a constant identifier there. And the vector coordinates can be constrained using inequalities this way. And all the symbolic constants, so the parameters here, the symbolic constants are also expressed, captured in some kind of closure syntax. So you have essentially the context, which describes everything that is symbolic, and then you have the quantified locally bound variables, I, J, K, L, that are constrained using inequalities and those symbols. So it's rather easy to reason about it, and there is a logic associated with this. It's called Presburger arithmetic. I didn't write the name anywhere, but unlike the main reason we are interested in that, and I will come back to that later, is that this logic is decidable. So most of these geometrical questions, so what's the intersection of two sets, is it empty, etc., this is decidable. There are algorithms that are more or less expensive, but you can actually answer those questions. If the expressions there were more complicated, like you were essentially reading stuff from a socket on the network, it would be very hard to statically answer the question. Or if you have polynomials, same thing, you cannot answer the question in general. Okay, so that's the main reason we are doing this kind of linear affine abstractions. So what can we do with that? Tiling. Back to the start. So this is, let's say, an iteration space, an iteration domain, two-dimensional. That's a bit simpler than the convolution before. You can see it as a degenerate convolution where you only look at the left element. So when you compute the next layer of, for example, of a neural network, you only apply a function to the element on your left. In general, you would typically look at all neighbors. In this case, it's a degenerate version of this. So you may want to carve some blocks, some tiles out of this iteration domain and execute them atomically. That's what we call a tile. So it's safe to do that because when you chain those tiles, you can see that there is no data dependence path going back and forth that goes out of a tile and back again. So the tiles are convex with respect to the data dependencies. So you need those iterations to, at least you need those 3 iterations to compute the 3 iterations of the next layer, but you don't need any of the iterations on the right tile or on the upward tile to compute anything inside. Okay. Yes, I think there was a question. Or... Yes?
So the arrows, they mean that from one dot you need...
Yes. So that means for this you need that.
Okay.
So think of this as one layer, or could be an image processing pipeline. So you're applying some edge detection after doing some Gaussian elimination or something. So each time you need the previous step to be completed before you can complete the next one, like mentally. But if you zoom in at every iteration, at the level of every iteration, you can actually be smarter than that. You can realize that you can complete a full block without actually touching the rest of the image. This is the case in this particular pattern because the dependencies only go to the right and to the top. If you have a more general dependence pattern, I will have examples of that. You may not be able to find tiles that are as simple as those ones. It's a simple example.
The arrow points to what you need?
No, it's the opposite. Yeah. The arrows point to consumers, producer-consumer. So for most people in the world, except for a few people I won't name, this is the semantics of the arrow. So if you look at the dependence graph in like SSA, use def chains, or whatever, or register level, more classical like scalar frameworks, that's what the arrow means. I know some people put the arrows in the other side, but I think that's utterly confusing. Okay. So that's obviously the kind of thing you want to do when you want to, for example, carve the computation to fit on the given cache capacity. So if you want to make sure that all this work can fit within a cache of a certain size, you want to carve a block, a tile, that's not exceeding, such that one row of this tile does not exceed the size of the cache. You also may want to do that for vectorization. So here it's pretty nice. You have 4 elements, so you can run in lockstep. This is like 4 additions in parallel, 4 multiplications in parallel, 4 additions in parallel, I don't know what, okay? These are typical steps you may want to take to vectorize the code and also compress the memory footprint needed to make progress. And this has a huge impact on performance. It can have several orders of magnitude difference compared to the original, like, naive program I've showed before. And there are multiple ways of modeling this in an affine, like, polyhedral framework. Typically, in general, as I said before, there are 2 steps that have to be kept as decoupled as much as possible. One is decomposing each dimension in stripes. And the second one is permuting the order of stripes. So in this case, we do both. We decompose both I and j dimension in stripes. And we also say that when we run out of iterations in one stripe, we don't continue with the next stripe, but we permute. We go to the next stripe of the j dimension. Okay? So there is some permutation involved of the indices. And maybe I could use the board here, because I don't think I have a slide with this notation. But assuming you start from an iteration space ij, when you apply strip mining, you typically get into a 4-dimensional space, which is I, jj, and j. And I and jj would be the big steps, the stripe steps. Essentially, they go from one tile to the next. And I and j would be the so-called point steps or point loops that go within the tile. Okay, the finer grain iterations. If you only do that, you just say, oh, I have a big dimension, I strip mine it into big steps and small steps. You don't change anything to the schedule. So you still, I mean, the schedule is represented mathematically in a 4D space when it was 2D before, but the way the memory is addressed is exactly the same order, essentially. But now what you can do is this. Okay? You can exchange 2 dimensions. You can say, oh, I want the schedule to be I, jj, I, and j. Same number of computations, but this time I'm doing exactly what is on the picture here. So I'm completing, basically at low speed, I'm striding over tiles, described by I and jj, and at fast pace, inside the tile, I'm iterating within every iteration, every point. Okay, so this is exactly tiling. This is permute. If you do both, you actually tile. So that's one trivial example of transformation composition that you can capture using these integer sets or these integer relations by simply saying, I'm changing the dimensionality of the problem, I'm permuting dimensions, potentially doing more than that. You could start adding constants, like to realign or to shift the dimensions a little bit. You can do all kinds of tricks, but it's very easy to reason about these compositions of transformations compared to think of doing that on the loops themselves. Figuring out how to recompute the loop bounds, etc., will be much more problematic. Okay, so this is just an example. You can do also loop fusion. this way. So think of another example where you have typically two very similar tiles as before, except that this time the dependence doesn't go to the right, it goes only to the top. It goes only upwards. But now you have two of these statements, not only, for example, you had S1 and S2 before, you could have a third statement, S3, that computes another level of a filter in the image. So you also have dependencies from statement S2 to statement S3, from one computational statement to the next. And one of the things you may want to do there is to bring the two tiles closer together. So instead of completely traversing this tile and then going to the next tile, you can interleave at fine grain at the point loop dimensions, so I and j and not II and jj, and say that I want to do 0 and 28, then 1 and 24, then whatever, okay? And by doing that, you may want to do even more crazy things. So I actually, if you look at the numbering of the nodes, I don't know if you can read it, it's a bit more scrambled than that. So it goes up this way, 1, 0, 1, 2, 3. But here it goes 28, 24, 20, 16. So it's a bit confusing. The reason is that this tile has been also permuted internally. So this is actually not ij, this is ji. So this tile goes from 16 to 19. So it's traversed in rows and not in columns. So you can do this kind of combination. So you can like permute locally the iteration space of one statement before fusing it with another statement. You can realign things before fusing, tiling, etc. So all these things commute essentially. It's just affine transformations that will compose in a natural mathematical way. And that's great, so it's very expressive, but you can think of now, what does it take for a compiler to decide what to do? It's becoming an interesting problem. So the compiler is now provided a lot of expressiveness to transform the code, very powerful tool, but figuring out the right combination of those transformations becomes a challenge. Even if you can do it, you don't know what's profitable, you don't know what's good. And there are lots of heuristics that have been designed in the past, so I just name a few of them, trying to maximally fuse, minimally fuse, to distribute, to vectorize, for example. And there are some alternatives to do that. And those are, of course, coupled with tiling and other transformations that are necessary for cache usage, for example. So I don't have time to go into the details of those algorithms. I'm just giving you some keywords so that if you want to find out in the papers that in the reference list you can find more information. But to summarize, the way we deal with program transformations in a polyhedral framework is to go from iteration domains to some kind of logical time abstraction by so-called affine schedules. So these transformations, these affine transformations, these linear transformations there, actually we don't represent them directly from program to program. We represent them from iteration domains, the iteration space, to some logical time. And in this case, you would say that going first through, how does it work here? Yeah, through j, and then j is the fastest varying dimension and I is the slowest dimension, would correspond to this time mapping. So you have a function that would go first through j. So you see that those three iterations of j are laid out consecutively over time, and then you go to the iterations of I. So you can build this kind of functional abstractions for the ordering of the iterations of the program, but there is a little bit of a problem there, because we want to stick with linear functions or affine functions. So we are only interested in affine schedules that assign logical dates to iterations that remain affine, that remain linear. And the reason for that, I will go back to it, I already mentioned it, we want to stick within the Presburger arithmetic logic, but why I will explain later. The constraint is that you want the affine schedule to look like this. So it has to be some constants multiplied by iterations, by the vectors that form the iteration domain, plus a big constant, or some sum of factors that are only constant numerals. And this is typically not the case here, because in general, if you don't know the shape of this matrix, if you don't know how many iterations of j there are, for example, you have to count them here. So you don't know how many iterations of j there are before starting the next row of iterations of j. So this function, typically presented like this, is not necessarily an affine function. You would have like the number of iterations of j times I plus j, something like that. And if you look at LLVM, that's how multidimensional arrays are implemented. If you have an array of unknown size, you get to linearized functions that do this kind of multiplications all the time. It's a complete mess for loop optimizations. So the trick is to use multidimensional time. So the abstraction for time is not these linear logical time steps. It's a multidimensional one. And you can see that as logically, for example, to model nested loops, you can think of I and j as hours and minutes, for example, okay, or days and seconds, or whatever. Except that you don't know how many minutes there are in a hour, or how many seconds in a minute. You just say, this is fastest varying, and this is slower varying. So you model this, we see that this can be very easily modeled in a linear algebraic or geometrical way. And the advantage is that now you can describe the ordering of those iterations, this just canonical ordering of the imperative like C loop nest, using affine functions again. Using linear functions, you don't have to multiply by the number of iterations, h minus kh or w minus kw. These things will never appear. You will never get these kind of products in the functions, which would not be linear. So this is so-called lexicographic ordering of time steps. So the geometrical abstractions for schedules, for affine schedules, is actually a function that goes from the iteration domain to these multidimensional time steps that are lexicographically ordered. So lexicographic, as I said, is like logical dates, like seconds, minutes, hours, whatever, except it's more like the dictionary, in fact, hence the name. You don't know how many seconds there are in a minute. Okay, so this is just an example. So. Except I'm a bit confused here. I think all the signs are reversed. So 0, 0 comes before 0, 1, comes before 0, comma, whatever crazy large number, comes before 1, 0, which is the next minute over the seconds, which comes before 1, 1. Okay? Sorry, all the operators are reversed. And this allows you to model like canonically this kind of multidimensional ordering in a linear way, and that's the graphical representation. In a multidimensional time, you have now the seconds and the minutes. So the seconds are directly mapped to the j dimension, and the minutes to the I dimension, and that's it. Okay, now you have just ij maps to ij. There is no magic, no multiplication with a big constant. So that's a very simple trick, but without that, we could not do much, in fact. And you can go one more step beyond that. You can try to model not only one statement at a time, but iteration domains of multiple statements. Like again, in the convolution case, you may want to model both S1 and S2, and try to organize the schedule of, so the logical dates of statement S1 with respect to statement S2, but at the iteration level. In this case, you want to say that for a given iteration of I and j, statement S1 always execute before statement S2 for any iteration of k and l. That's different from saying that S1 executes before S2. It's not the case. S1 and S2 are actually interleaved over time, but more specifically, reasoning at the iteration level, you can say, symbolically in I and j, I know that the precise iteration of S1 executes before any iteration of S2, any meaning for any value of k and l. So this is a very simple logic formula that says for all ij, for all kl, the logical time of this is before the logical time of that. Okay. Okay. So I prefer to skip the bottom thing and go to this slide. So this is a trick that we use, more like a convention that we use to encode those logical dates, those multidimensional logical dates in practice. Again, for this example, instead of counting how many steps there are, like how many statements there are at a given depth in the loop nest, we introduce additional like constant dimensions this way. So for example, we would say that S1 and S2, they execute within the same loops I and j. So we model this by starting lexicographically from the left with I and j. And then S1 always execute before S2. This is 0 is always less than 1. And then these are don't cares. You can put whatever values there, like 0 or whatever, doesn't matter, because the lexicographic ordering is always guaranteed by this 0 being before 1. And then K and L describe the iterations of S2. So by logically ordering S1 and S2 this way, you know that iterations of S1 are ordered according to I and j, S2 as well. S2 is also ordered with respect to K and L, and among the two, S1 is always executed before S2 for a given iteration of I and j. Okay, so we have all the information captured this way. So this is no big deal. When you're used to it, it's completely trivial, but okay. For some reason, you need 5 dimensions of time now to model the program. Okay? More complex. How much time do you have? Okay. Matrix product, but twice. So 2 matrix products in a row. So this is a program that computes A times B, stores it into a temporary matrix TMP, and then multiplies again TMP with C to store it into a matrix D. So the sizes are, these are rectangular matrices, so trust me, the sizes should be compatible. So here there are many things you may want to do to this program. So one of the things that's not represented here because it's bloated otherwise in syntax is to do tiling. So you may want to add many loops like II, JJ, KK, so you get now 6 loops nested to represent blockwise matrix multiplication. I want to spare your eyes, so I don't show that. But even without this, you still have lots of combinations. So should I initialize everything beforehand, like do all the initialization of TMP and D beforehand, or should I somehow fuse it such that I'm doing it interleaved with the accumulations in TMP? Should I try to fuse further and actually realize that, oh, I could do that before, or I may want to start operating on a row of TMP before completing all the iterations of I, and I may actually start doing some of the iterations of the second matrix product. So there are all kinds of combinations you can do. And the question is, how do you model this as an optimization problem? How do you find the best combination of transformations? So what permutations of loops and what fusion of loops are profitable? And how is it different on the GPU, version 1, version 2, version 3, on the CPU with one processor, 2 processors, one vector length of something, etc. So this is exactly the kind of problems that we try to solve. Okay. So you have tiling decisions that I didn't show, and then all these permutations of loops, fusion of loops to try to essentially match the producers with consumers as tightly as possible. You don't want to essentially waste cache resources. You want to use different levels of parallelism, etc. This all amounts to permuting loops, fusing those loops, etc. And this is very easily captured in this representation. All what I just said, except tiling, because I didn't want to blow those vectors again, amounts to permuting components in these vectors. And some of the ones become 0, some of the zeros become 1s, and that's just a couple of examples that you can model using these affine schedules. For example, this one. So the difference here is that there is an outer fusion versus an inner fusion. So outer fusion means that we would bring the second matrix product and interleave it with the first one at the level of the outer loop, of the loop I. So you can see that here. The first component becomes 0. Initially, it would have been 2 typically. Now you make it closer to the source, and you try to initialize TMP and D together, and then you try at the row level to interleave computations of TMP and D as well. And you can do something else. You can say, oh no, it's the opposite. I want to actually separate the initialization from the rest, and you would end up with this kind of scheme. I don't go into the details. For some reason, the second one is twice faster on a 4-core CPU, typical modern Intel machine with multiple threads, with 4 threads. Okay, so these are the kind of problems that we are trying to solve here. So I'm not going to give too many more examples of the kind because this is quickly frightening. But I want to convince you that the problem is actually mathematically simple at this point. In general, we are looking for functions like this, which map iterations to logical dates, vectors of iterations to logical dates, which are also vectors. Sometimes we want to go a bit beyond that, so we want to have, actually we encode tiling using integer divisions or modulo operations. So you may actually want to capture relations rather than just functions. But that's just a detail. I'm not going to go into the details on this, but in general, these are not only functions, these are actually relations from iterations to logical dates, just for the record. And the main optimization problem here is solved with the so-called polyhedral affine scheduling algorithm. Affine or polyhedral scheduling algorithm. And there are multiple variants of this algorithm, but generally the idea is to iteratively refine the logical dates, the logical functions, from doing it dimension per dimension. So you do it, first of all, for the outer loops of the generated code, and then iteratively you refine for the finest grain computation like vectors or instruction level scheduling. And you try to optimize for different criteria, so that again depends on the heuristic. But you try to bring producers and consumers close together so that you exploit locality. You don't want to waste cache resources. You also try to, when the distance of dependence, I didn't define this term, but essentially is how many iterations you go from one producer to a consumer. When the distance becomes 0, that means there is no loop iteration in between the producer and consumer. That means the loop can be run in parallel, essentially. So there's a simple way to model parallelism, and you want to maximize the number of loops that are parallel, typically and expose them later to the hierarchy of the processor. So that depends. If you have a CPU or GPU, you may want to have more than one level of parallelism. So there are all kinds of tricks there, but essentially that's what you try to do. Of course, you cannot do that completely free. you have always to mind about dependencies. You have to always to look at what's legal, what's correct. And here there is a very nice property, is as long as the dependencies are going forward in time, you're safe. And that's very intuitive. So there is an old result from Lamport in '74 that proves this in a kind of general setting. As long as the dependence, the producers are executed before the consumers, whatever you do is always safe. There is also the so-called Bernstein conditions in parallel programming, but these are all trivial things. It's only this intuition. Okay, you don't care about the ordering of all the numerical operations going on. You don't care about loop iterations in which order they run, as long as every value is defined before being used. So exactly like in SSA or like diffuse chains in compilers, except that now this is operating at the level of individual iterations, and iterations meaning vectors. So you have to check that the dependencies go forward in time. Forward in time means lexicographically positive. So this is nice because being lexicographically positive is actually a simple geometrical constraint to apply to the problems that we are optimizing. And there is also a related definition. When you realize that all dependencies are actually non-negative, so they don't have to be strictly positive, they are just non-negative, it's slightly weaker. That means you can actually permute the dimensions. You can run in like I first and j inside, or j first and I inside. Doesn't make a difference, because whatever permutation will still result in forward going iterations. You will always run the producer before the consumer. So one of the objectives of optimization problems is actually to look for not necessarily minimizing the number of steps or this kind of maybe more intuitive goals, but instead just trying to make loops permutable. If you have permutable loops, it's okay. We can do tiling. We are going to fit the hardware constraints. We can do all kinds of things. Okay? So this is another important criteria that is being addressed by affine scheduling algorithms. So that's an example. So this is a valid dependence vector. So the vector between the producer and consumer, if it's 0, 1, 0, 0, is fine. This is lexicographically positive. This is also valid. But that one is not valid because lexicographically, the first non-zero component you encounter is -1. So it's negative. It's not going forward in time, it's going backward in time. Okay, so for example, in this case, all loops are permutable, all dimensions are permutable. You can do tiling in a completely free way. In this example, you can tile only the outer 2 dimensions, but not those because of the negative value here. And in this case, the third case, you cannot tile anything because it's not even correct. Okay, I'm skipping the details. There is one more trick I want to mention, which is actually very important. And if you look at the literature, this is like half of the papers are on this problem. The main problem is that from this very nice picture before, like we want to optimize whatever logical functions that are lexicographically positive, etc. The main problem is that the general form of the schedules, as I mentioned before, is a linear function. It's an affine function. This is actually an unknown function. It's the function we are looking for. When you optimize the code, finding like parallelizable, cache-friendly, vectorizable program amounts to finding such functions. The problem is that this function is actually unknown, and there are 2 unknowns factors in every term. Both the iterations, in this case I is the loop iterators in the iteration domain, or the symbolic constants, the parameters, are unknown. And also the coefficients of the affine function itself. So you're looking for a function, meaning you're looking for A and B, really. Okay? How to actually linearly combine iterations and symbolic constants into some logical dates. And this is not an affine function anymore. Okay? It looks affine, but only when you know A and B. If you don't know A and B, it's not affine anymore. It's a polynomial of degree 2. Okay? So, for example, trying to minimize the distance between producers and consumer, assuming you have a dependence from a statement R to a statement S, you want to minimize the number of steps, for example, it takes to, that's kind of an approximation of how long the value will be stored in the cache. This is not an optimization problem that's easy to solve because the T function is not affine, it's not linear. So there is a general trick to solve this problem. It takes 2 steps. Typically it takes bounding this difference with some other hyperplanes or some other linear form, and converting these constraints with a geometrical result called the affine form of the Farkas Lemma. It's just a fancy name for actually a rather profound geometric intuition. Maybe I can just draw the picture so that it will be less obscure. what you end up doing in general when you optimize programs in this framework is you have constraints. So these are, for example, dependencies. These may be some cache size or whatever. So okay, so these are all constraints. And you're looking for a function t. Actually, t s minus tr. This is your function. You want it to be positive. Okay, so for every point that satisfies, every vector that satisfies those constraints, so those vectors practically they will be actually made of iteration vectors of both s and r, so two statements, two instructions. You want this function to be positive, but the function is the unknown. That's what you're looking for, because that's exactly the result of your transformation. And the trick is that with the Farkas Lemma, you can convert the representation of a function that is positive over a system of linear inequalities. It's equivalent, this is an if and only if condition, to expressing ts minus tr as a linear combination of the normal vectors to these constraints. I call them n this way. Okay, so this is just an informal way of setting it, but and these are positive coefficients. I don't know if you've dealt with Lagrange multipliers at some point in your math courses, but it's a similar property, except it's an if and only if condition. So this is a very nice way, because the very nice result, because when you do that, now your unknown function that was actually a polynomial becomes just searching for some coefficients that now in a linear form. So there is a trick, essentially, which I don't want you to spend time on this in this room unless you're very interested. This is the kind of level of detail I cannot go through. That makes this geometrical problem, which looks very frightening, actually very simple in terms of linear optimization. And in the end, what people do is that, okay, now we have essentially an optimization problem that can be solved using linear programming, or in many cases actually integer linear programming, which is not that nice, it's NP-complete, but there are good tools for that. And you can actually optimize the locality and tiling and all kinds of things by converting this problem through this lemma and then applying linear objective functions on it. So I'm skipping that. There are ways to go a bit further than that. Essentially, you can not only model iteration domains and schedules using affine functions, but you can also combine them with more imperative, more familiar, let's say, syntax or inductive semantics. For example, if you want to parallelize and optimize matrix product on the GPU, you want to do all kinds of things. Intuitively, you want to fuse loops, you want to tile loops, and you want to decide what goes to the threads and to the blocks. You end up doing this kind of linear transformations there. There are lots of divisions by 32 and 16 because these are the block sizes that map well to warps and threads and blocks and whatnot on the GPU. Many of these decisions are actually not geometric. They are actually very GPU specific. You want to say, oh, this is actually running in sequence on threads or on blocks, or there is a data transfer that takes place from global memory to shared memory or whatnot. If you don't know CUDA, it's not important, but there are all kinds of things to do that are GPU specific, and there are ways to capture these things in a more syntactic way together with affine schedules. So although I said, yeah, it's perfect, you can reason about programs in a geometrical way, in practice, the tools don't do that. They do a mix of like more syntactic, like AST style, and geometrical modeling. And you can do this. It's called like schedule trees in the ISL library I mentioned before. And then there are a few problems to be solved. So you're almost done, but not quite. Geometry is great, linear optimization is great, but at some point you want to run code, okay? So you have to generate loop nests again. It's fun to reason about these functions there, but at some point you want actually to iterate on I, j, k, and access memory efficiently. And that's called AST generation or code generation in the Polyhedral framework. And the general problem is that given iteration domains, given these schedules that we spend so much time defining and computing, how to generate nested loops that actually traverse the iteration domains in the prescribed order. So the schedule tells you the logical dates that are ordered lexicographically. You actually have to scan those iteration spaces, iteration domains, according to these logical dates, because that was the whole point. And this is not a trivial problem. It's reasonably simple when you have only one statement, but when you have more than one statement at different nesting depth, think of matrix product or the convolution, there is an initialization statement that has only 2 loops, and in the convolution you have the accumulation statement has 4 nested loops. So geometrically scanning those points in Polyhedral is actually a difficult problem. And it was solved the first time in a complete way in 2004 by a colleague, Cédric Bastoul, and then it was refined several times since then. And the technique that's implemented in ISL, I contributed to it, was published only 4 years ago. So it's not a very complex problem, like conceptually speaking, but to generate actually efficient code, you want control flow to be simple. You don't want to, of course, execute stupid stuff like unnecessary iterations in loops. You want to be very tight with respect to the actual points that are in the iteration domain. This is actually non-trivial. Okay, and just maybe going back to, I promised you I will tell you why do we care about affine schedules after all. So I already said it several times, but let me really insist on that. Yeah, essentially, in general, if you look at code generation, I think it gives you a different picture of how essential it is to have affine schedules. Think of code generation as a function inversion problem. So if you want to scan the iteration domains that represent all the work that is being computed in a program, in the loop nest, it means scanning time, like one logical step at a time, and figuring out which iterations of which statements execute at that particular instant. So it's like inverting the schedule function. So you have a function that goes from iteration domains to time. If you want to generate code, you have to do the opposite. You have to go from time and figure out what code should run at every given time step. Except that this function is symbolic, is described intentionally with systems of constraints, so it's a little bit of a difficult inverse problem. Okay, and in general, actually, that's one of the reasons we want schedules to be invertible, because we want this to be like non-ambiguous. It's not a strict restriction, but it's typically one thing we want to do. And this is just a crazy example, but if you linearize everything, I told you not do that because we use multidimensional schedules, but if you linearize everything, you can have like systems like this. Oh, please tell me what iterations I and j, parametrically in some symbolic value n, execute at time t0, t1, t2. Okay? Okay, so sounds fun. Unfortunately, that was one of the Hilbert's problems that were defined at the turn of the 20th century, that were later proven, much later actually, as non-decidable. Okay? So we can't do that in general. So code generation is in general not decidable. That's tough. That's only in the general case. So only if you have general polynomial. If you have affine forms, it's no problem. It's exactly the problem I was telling you before. So it's a bit tricky to generate good code, but there are systematic ways to do that for polyhedra. But if you have general polynomials, for example, if you had linearized those multidimensional schedules, it's absolutely, it's a very complex problem. Okay? So there are heuristics in some cases. So I don't know if you have used SMT solvers, for example, like Z3, etc. So there are some ways to, in some cases, reduce or symbolic reasoning system, like Maple or something. But in general, it's not decidable. So you have to, if you want to build a compiler, I would say that solving non-decidable problems is not necessarily a good idea. So you'd prefer to find an approximation or some simplifications that make it slightly more friendly. And that's the main reason we limit ourselves to affine forms, because these kind of problems go away, and you have much simpler problems to actually, maybe it's combinatorial, you may have to do ILP, like linear programming, but it's not that bad in practice. Okay, so in the affine domain, there are techniques, typically Gaussian elimination, you all know that, when you have only equations, so it's like a cubic algorithm, it's very simple. If you have both equations, like equalities and inequalities, it's a bit more tricky. You may have to do linear programming or Fourier-Motzkin elimination, which is just an iterated like substitution algorithm. It's very easy to understand. Unfortunately, both of them are exponential in the worst case, but at least it's possible to solve these questions. So there are actually special cases I mentioned that can be solved. So I'm just listing some references there if you're interested, but it's mostly for like mathematical curiosity, because no tool actually does anything sensible with that for now. Let me conclude. Let me see. I think I can. I would rather. Yeah. I think I have to go through the. Yeah. Let me finish with that. And then I can go with some concrete applications, like to machine learning and more interesting domains tomorrow. there is one more thing that I didn't really explain is how do we define these dependencies? So how do we know that some computation depends on some other computation? And that's the main constraint that makes the whole thing like semantically tricky in terms of compiler construction. That's what we typically care about first. Profitability is a difficult issue, so what's good for performance is an issue. But even more important, what's correct, that's what we should care about. And in the end, it's very similar to what I described for scheduling, except now we have to deal with a different relation, which is between iteration domains and memory. So we have to model which iteration vector accesses which array element, typically. And so basically, what the key here is order of iterations, as I mentioned before, don't matter as long as the results in memory are the same. And so we have to model the memory accesses, and we call them access functions. Typically, every statement that's not a loop, every computational statement, is defined by which references to arrays it holds. And we make some simplifying assumptions there. So we assume that arrays are accessed in a linear way, or affine way. So we don't necessarily, there are some generalizations of this with approximations, obviously, like what you would do in static analysis. But as a first, like for presentation purposes, I'm assuming there is no aliasing between pointers. They're just plain nice arrays. And all the subscripts are affine, or like in the cases I was showing before, typically like just I, J, K, simple things like this, or I plus J, or things like that. Okay, so as long as array access functions are affine, you can do the same as before. So you can represent those functions as a relation from iteration domains to some logical arrangements of memory. So memory is very easily modeled as an array, as a multidimensional space, like as many dimensions as the arrays typically, and that's no big deal. And data dependencies are derived from those access functions by equating the accessed elements from two statement instances. So if you have one statement that writes into memory, a statement that reads from memory, you look at those precise instances, so the iteration vectors, which iterations correspond, actually access the same element, and you say, oh, maybe when I and j are equal to I prime plus 3 and j prime plus 4, that means statement s and s prime access the same element, essentially. So you write equations like this that tell you that two instances of two statements access the same array element, and you reason symbolically about that. So that's a typical geometric problem, which tells you I have those two domains separated, one for statement s and statement s prime, and I want to bring them together, adding constraints that some linear functions, some linear forms are actually equal. This is typically one of the things that a library like ISL can solve for you. It involves potentially complex algorithms, but it's decidable, and in practice it works pretty well. And then you can do more than that. You can also ask for these accesses to be actually ordered in a certain way, because that's everything that matters in the end. And this boils down to expressing the lexicographic order on the iteration vectors. We have already seen that before. Okay? So the only novelty here is that you add these constraints that two statements instances actually access the same element. They belong to the same to different iteration domain, but they have to access the same memory element. Okay, so I'm skipping the example. So this is very easy in terms of geometry, as I said a few minutes ago. What's great is that correctness, as was already shown on the example before, is essentially reduced to figuring out if a vector is positive, or at least non-negative for permittability, or positive for actual dependent satisfaction. So if you want to make sure that something happens before something else, you just look at the leading non-zero element in the vector, and if it's positive, you're fine. Okay. So that's very easy to model, and that's why the transformation problems are not very difficult to prove correct also, or in practice, most of the effort is on profitability, so figuring out what's good, what's efficient, and not so much what's correct. Okay, that's it. So I suggest to stop here, or I don't have a choice actually. Tomorrow I will show you how more like this theory boils down if you are in the context of PyTorch or TensorFlow and try to schedule tensor operations on a GPU or something like that, and how you construct a compiler using these principles. So there will be less math and more performance graphs. Thank you.
Back to the slide with the Farkas Lemma.
I realize I forgot to add slide numbers. I'm sorry about that.
What's nonlinear here?
What's what? Sorry.
What is nonlinear?
Yeah. So this is nonlinear because this is nonlinear. A are the coefficients we are looking for. We are looking for affine schedules, and they are defined by those A and B coefficients, and D as well. So that's fine. These are precisely what we're looking for. The problem is that I and P are symbolic expressions. I mean, they are the loop counters. So the unknowns are really A and B, but they are multiplied by non-constants. So it's very frustrating because we are almost there. But in fact, it's okay. We are really there, but it's up to some. It's called a duality result in geometry. But it's a very simple, practically simple to implement transformation. But the reason it's correct is mathematically quite deep. In fact, I have no clue actually how to prove it. We just use it every day. That's fine. Yep.
Is there a textbook that brings a lot of these things together?
Great question. I'm always very embarrassed when I get it. No. So Google is not explicitly paying for one, but I understood that would be appreciated at some point. So, especially since we're supposed to make it one of the bases for a new generation framework I will talk about tomorrow called MLIR. We should have some documentation that's accessible to everyone. So I'm not sure all this math really makes sense to engineers building Polyhedral compilers. I think the building blocks can be operated at a higher level of abstraction, but still, it would be good to have something. Yep.
I have one that I don't know if it's really, because I'm just not sure what the tiles they. So you show the diagram of the tile, do you create those tiles?
So, yeah, I didn't really have an example for it, but when I say this is where the tiling comes into play. So, in practice, what you try to do when you look for these affine scheduling functions, you're looking for these kind of properties. So, some of the coefficients should be permittable. Some of the dependence coefficients should be permittable. So, you look for an affine function that schedules iterations over time, such that dependencies for all the statements involved in the computation actually always go forward, irrespectively of which computation you choose. When you have this property, so you precisely point out which dimensions actually commute, and then these are the levels where you can apply tiling. So typically tiling is not modeled directly as the result of these problems. You don't actually get tiling out of this directly. You could, but it's kind of cumbersome. Instead, let's try to make things permittable, and I didn't have time to explain how the heuristics to make permittability a first-class objective is really included. But when you get this permittability, now you can do tiling for free. Okay,
but I'm not sure, if you have two statements that have this coordinate, identically the same tile, what does it mean for the two statements?
What does it mean in what sense? In terms of code or properties? So maybe you get this kind of interleaving. So, for example, if you, or maybe this one just, when you are within a tile, the fact that two statements are scheduled in the same tile means that you are going to go from one statement to the next, let's say, close by over time. You're not going to traverse the full image, for example, before going to the next iteration. So imagine this is a producer, this is a consumer. You don't want to scan the full row of the image if it's large, because if it's large, it won't fit the L1 cache, for example. You want to scan only a small number of iterations before going there. So in terms of code, it means that the two statements are sequenced deeper into the loop nest, not at the outermost level. Syntactically, I think it's much easier to reason this way than in terms of loops.
Did you say you were going to talk about MLIR?
Yeah, tomorrow we'll talk about MLIR and tensor comprehensions, which was a project at Facebook before, which also influenced some of the MLIR work.